Now, the PIC has a built-in analog to digital converter. A lot of microcontrollers have A to D converters built into them. So we'll take a look at it a little piece at a time. Now, this ADC has 8 different channels, which means that it can represent, or it can look at 8 different analog inputs. Now, it can only see one of those at any given time, but it can look at 8 different inputs. And you might notice that some of these pin names have 2 different names. Here's analog input 7, which has another name, RE2. Well, if you remember from looking at ports, RE2 is bit 2 of port E. So we have a port that has dual purpose. Okay, it can either be a general purpose input-output port, or it can be used as an analog input. We can define which one that's going to be. So we see that we have 3 bits of port E that can be used if we want them to as analog inputs, and we have 6 bits of port A, bit 0, 1, 2, 3, and I guess 5 bits. 5 bits of port A, 0, 1, 2, 3, and 5, that can be used for our analog inputs here. There's something inside the A to D converter called a control register. There are a couple of control or configuration registers, and these tell us how this ADC is actually being used and what configuration it's being used. There are 3 bits that are called the channel select bits. So these 3 bits tell you which channel you were looking at. So if we were looking at analog input 0, I would write 0, 0, 0 to those 3 bits. If I wanted to look at analog input 7, I would write 1, 1, 1 to those 3 bits. We'll take a look at that whole register in a couple of minutes. I can also have different types of reference voltages. So here I see a couple of single pole double throw switches that are built into the chip. Okay, and I see a couple of port configuration bits. There are 4 port configuration bits, PCFG3 down to PCFG0. Okay, those define the 4 possible, the different possible states of those 2 switches. So you can see that I can use VDD, that's my voltage supply, my supply voltage for the microprocessor itself. So that would be probably my 5 volts. I can use VDD and VSS for my signals. I can use, let's see, going up here, I can use VREF plus, that's an external pin that has multiple purposes here, but I can use that pin as a reference, my plus and minus references there, okay, or I can use some combination of those things. And my port configuration bits will define which of those we're using. I'll get more into the detail on those bits in a couple of minutes. Okay, here's a couple of control registers. ADCON stands for Analog to Digital Control Register, and these define how this A to D converter is going to be used. So we have 2 control registers, ADCON 0 and ADCON 1, and they have a bunch of different bits, and we'll talk about them just a little bit at a time. And I'm only going to go into a little bit of detail. I won't go into every possible combination of these, but you can look at the PIC reference sheet for complete details about these 2 registers. So let's look first at the clock select bits. The A to D converter, just like a microcontroller, needs a clock pulse. Clock pulses keep everything in synchronization. So like a drummer in a rock band keeps the whole band in sync so that everybody is strumming on the right chord, on the right beat, and things like that. Well, a microcontroller has its own clock signal that keeps all the data transfers synchronized, and the A to D converter uses a clock signal as well. And there's different ways that we can configure the clock. These 2 bits tell us how that clock is going to be configured. Okay, these 3 bits are our channel select. I talked about those before. We have 8 possible analog channels that we can read, so these 3 bits tell us which one we're looking at. This one is called the go done bit, and it actually serves 2 purposes. We control that. We can pull it high to tell it that we want the A to D to start a conversion. So when this bit goes from 0 to 1, it makes a low to high transition, then we're telling it, I want you to start a conversion. Then we can also look at this bit later, because when the conversion is complete, it will reset this bit back to 0. So the done has a bar over it. That means it's an active low. So when it resets this bit to a 0, it tells us, hey, I'm done with the conversion. Now you can read it. So to do a conversion, what you're going to do is write a 0 to this bit, then write a 1 to this bit. That causes this to go from low to high. That's the low to high transition that starts a conversion. And then you sit around and you keep looking at this bit and waiting for it to go back to 0. And when that happens, it says, hey, I'm done with the conversion. I'll show you the software for that in a few minutes. Now, You don't always use the analog to digital converter, so if you're not using it in a particular application, you can just turn it off, and that conserves power. A lot of microcontrollers run on battery operated systems, and conserving power is very important in a case like that. So we can save a little power by turning that off. Now this chip has a 10-bit analog to digital converter. Now remember that the PIC is an 8-bit processor, so it has 8-bit registers. So it's actually going to take 2 registers to deal with a 10-bit number. And that's going to be the A to D result registers. A to D result high and A to D result low. So that's the high byte and the low byte. Okay, this bit right here, ADFM, when it's a 0, that means that the converted result is going to be left justified. What that means is most of our result is going to be in AD res high, and then the last 2 bits are going to be up here in AD res low. Now, we can actually just ignore these 2 bits and pretend that this is an 8-bit analog to digital converter and just use the AD res high result. That's what we'll be doing in our application, because we don't really need 10 bits. Okay, this is one of the clock select bits. We'll talk about that a little bit more later. And these are port configuration bits. Okay, these are 4 bits that define one of 16 different configurations for this port. So let's take a look at that. Here are all the different combinations of these 4 bits and what they represent. And I've highlighted the one that we're going to use, it's most likely we're going to use. This has only one analog input, so we're using analog input 0. These other ones we're going to use as digital. And we're going to use VDD and VSS as our reference voltages instead of providing separate reference voltages. And that's all we need to know. To initialize the analog to digital converter, we're going to write a byte to each of these 2 registers. So this would be the configuration word for one of the registers. This would be the configuration word for another register. I went through it in previously how to get these bits. This is the software that will do this. So I'm going to take ADCON, write 0B, that means it's a binary number, and here's the binary number. So ADCON 0 is assigned this binary number right here. And I put a couple of comments to indicate that that means I'm going to use the system clock divided by 32. I'm going to use channel 0 only, and that last bit says don't turn on the A to D converter yet. Okay? You don't usually want to turn that on until you've finished writing to all of the control words. So then I'm going to write to ADCON 1, that's my other control word. Okay, this says take the result and left justify it, use one analog input. I'm going to use VDD and VSS as my references, so that's what those bits mean. It's a good idea to put a comment indicating what those meant. Okay, so over here is where I figured it out. Those are the binary numbers, and then here's where I put it in software. And then after those 2 registers are written to, now you can turn the ADC on. Okay, this is a single bit. Whoops, there it is. There's the AD on bit. And sorry, and this is what turns it on. To start a conversion, I mentioned before what you need is a low to high transition. So you want a low to high transition on this go done bit. And the way you do that is there's a predefined word, the compiler already knows it, it's called go done. Okay, that's not pronounced God one, it's go done. Okay, so we can say go done is assigned the value 0, and then go done is assigned the value 1. That causes this low to high transition, and that's what triggers a conversion. That says start a conversion. Then what we do is we sit around and we wait for this bit to go low again. The microcontroller itself will force this bit to go low, and that tells us that the conversion is finished. And the way you do that is you sit here in a little while loop that says while go done is equal to 1. So as long as that bit is high, we're going to sit here in this while loop. Notice it doesn't really do anything. That's just a comment. It doesn't do anything. But while that signal is equal to 1, it sits here in this loop. As soon as that signal goes to 0, this condition is false. It breaks out of the loop, and then it goes down below. And then reading the result, we read the result from the A to D res high and then 2 bits from the A to D res low registers. And if we're only interested in an 8-bit analog to digital converter, all we have to do is take our AD res high register and assign it to a variable that we'll call analog value or actual temperature or whatever. So here's the software to start, wait, and read. Okay, here's starting a conversion. Go done is assigned 0, and then go done is assigned 1. That gives you the low to high transition. To wait for a conversion, you do this little while loop that does nothing except wait. And then here's how you read the 8-bit analog to digital value. So print this page right here from your notes. So there's everything you ever wanted to know about analog to digital converters, maybe even a little too much. See you next time.